Hello everyone, welcome to part 3 of video lecture on counters. Okay, so what we've seen so far is a counter, one bit counter, right? Something like a single T flip-flop. When you connect it in toggle mode, you can see that whatever be the input frequency, that is being divided by 2 by it. Hope you remember this circuit, right? So some input clock I am applying, so the output, when I observed, I saw that it is of frequency half of the input, and this concept we saw like it's some kind of an one bit counting, because it's changing from 0 to 1, 1 to 0, like that. Now we constructed this using T flip-flop. Now the question is, can I construct the same circuit using a D flip-flop? Okay, and let's try that. So what is our D flip-flop? D flip-flop, T is toggle mode or retain mode, but D means whatever be your D, that will come in the output Q, and there is a Q complement also, right? So what you can do is, what I can tell you is like, you just take this Q, or you take this Q complement and you connect it with this D. I hope you remember in the previous T flip-flop implementation, we connected T as 1. I mean, we fixed it like that. We connected it in the toggle mode. So here we are configuring like this. Then we are applying a clock pulse. Okay. And now you can see that if you are observing this clock, some clock you are applying like this, right? And now during the positive edge of the clock, suppose initially this Q is in some 0, right? During this positive edge of the clock, initially it is 0, right? So as Q is in 0, see what is your Q bar? Q bar is 1, and that one is coming here, right? That one is coming here. Now during this triggering positive edge of the clock, this 1 will come as Q. So this 0 will change to 1, right? Now what will happen? So Q is 1, so that Q bar is 0, right? That 0 is now waiting here. So whenever it is reaching the next positive edge of the clock, this 0 will come as output, so that this 1 will change it to 0. Now your Q is 0, so that your Q bar is 1, and that 1 will be waiting here, right? That 1 will be waiting here. Now for this 1 to come out, next positive edge is needed. So whenever it is reaching the next positive edge of the clock, this 1 will come out. Now you can see that it is just toggling, right? 0 is changed to 1, 1 is changed to 0, right? Same toggling I implemented by D flip-flop. What I done is that Q bar I connected to this D, so that it is doing the same. So this is equivalent to, this one is equivalent to what? Our T flip-flop connected in toggle mode. Hope you remember. Both circuits are same. So here also this Q is, if you observe this Q, it will keep changing like 0, then 1, then 0, then 1, like that. The same behavior you can observe, okay? Same thing. Now if you want, you can do it. And so here as Q bar is available as a complementary output, we can make use of it. Now equivalently, if you want, you can draw like this also, what I was doing. I am not disturbing that Q bar, or assume that Q bar is not available. Same effect only, I just trying to show you a different circuit, that's all. So here I am using a NOT gate, and that output I am connecting here, right? Now instead of that, here I taken Q bar. Both are having the same effect only, and this Q I am taking like this also. And if I am applying a clock here, definitely I will get the output as 0 changed to 1, 1 changed to 0, or frequency half of it, right? So you will you know how it is working. So with that assumption, I proceeded like this, okay? So this is the configuration we saw. So Q bar we are connecting, so that the output frequency will be half of the input frequency, f by 2. F by 2 hertz is the output frequency, means the input frequency is f hertz. So that I have a clock. So if this clock is of some f hertz frequency, so that so there is some mistake, sorry for that. I've taken from somewhere. If this is of time period t, you can see that the time period of this one is 2t, right? So that its frequency will be, f dash will be of 1 by 2t, that is nothing but f by 2, this much hertz. Yeah, there is something called a duty cycle that I will maybe I may discuss in the next video. Yeah, that about it. Anyway, duty cycle concept I will tell you in the next video, okay? That is again another application of T flip-flop. We will see that. Now divide by, this is again the same circuit. I taken some different figure. This Q bar you are connecting, or what you can do is this, you can negate this D if Q bar is not available, something like that. So that way also you can connect. Same circuit I shown different diagram. Now the question is, can I use this JK flip-flop to construct a divided by 2 counter, or divided by 2 device. Okay, so you can do it because T flip flop is nothing but a JK flip flop where both J and K merged, right, as T, and when you are giving the T is equal to 1, so by default you fix you fixed your T as 1, right? So here also J and K you apply 1, so this will be now equivalent to your T flip flop, same thing, right? The T flip flop, the input is 1, both are same, and you are applying a clock, so that this will also divide the frequency. So if here the time period is T, I am repeating this concept again and again, this will be 2T, so that if this is of f hertz, this will be of f by 2 hertz. Yes. So what about the conclusion? What we discussed so far is, the circuit we saw so far is something called as a frequency divider circuit, and it divided the input frequency by 2. So we just used a single flip flop for that, for achieving that. Okay, and it is also called as modulo 2 counter because it's going through two states, 0 and 1. Hope you remember that modulo 2 counting, 0 then 1, and this transition is happening during the clock edge. It's also called as divided by 2 counter. So modulus, what is modulus of a counter is defined as a number of unique states that a counter will sequence through. So how many unique states? Here it is sequencing through 2 unique states, right? So that's why you call it as a mod 2 or modulo 2 counter. So in general, if I have a counter that is going through say 0, 1, etc., or state 0, state 1, etc., some state k minus 1 states, something like that. Okay, 0 to k minus 1, totally k. So this is a this is having say k unique states, right? So what I can call this one is mod 2, mod k or modulo k counter. So that will go through this kind of a state sequence. Yes. Yeah, that about it. We will see some variations and all and generalization in the next video. Thanks for watching.